In section 7.1, we're going to be looking at graphing exponential functions. First, let's get an idea of where an exponential function can be found. Got an example here. 5 bacteria in a culture, double each day. So on the first day, day 0, there was 0. After the 1 day has been completed, there's twice as much, so that there's 10. After 2 days, there's twice as much, so there's 20. 3 days, there's twice as much, so there's 40. Graph the population of the bacteria, B, as a function of time and days, T. So what we're going to have here is, you see as the days go up, it keeps doubling or multiplying by 2. So we see that this is really 5 times 2 raised to the first. And this is 5 times 2 raised to the second. Here we got 3 of them, so it's 5 times 2 raised to the third. After the 4th day, it's doubled 1, 2, 3, 4 times, so it's 5 times 2 raised to the 4th. After the 5th day, it's doubled 1, 2, 3, 4, 5 times, so it's 5 times 2 raised to the 5th. So what we see here is we have a function of the style y equals 5 times 2 raised to the x. Or in terms of our variables, the bacteria equal 5 to start with times 2 raised to the t. And we can check this. When t is 0, 2 raised to the 0 is just 1. 5 times 1 is 5, and we're still good there. 5 times 2 raised to the 0. So our basic functions normally look like this. Some constant in front for either a vertical stretch, that's normally the starting value. You have the base, which is how much is being multiplied by each time. In this case, it would be multiplied by 2. There's sometimes a shift left or right. So the x plus h might be up here, and then the plus k. Normally, though, we don't put the values up here, the plus h up here, because what we can do here, instead of saying the base raised to the x plus h, we can actually rewrite this. For example, if I have 3 raised to the second times 3 raised to the fourth, that's going to give me 3 raised to the 2 plus 4, which is 3 raised to the sixth. Replacing that with x, 2 raised to x plus 3, I can change that into 2 raised to the x times 2 raised to the 3. Because we know that we would just have to add those together like we did up here. But 2 raised to the 3 is really 8. So I can rewrite it 8 times 2 raised to the x. Anyway, that's something we can do. So it's normally of this form right here, where the starting value is right here, the a, in this case the 5, times the base raised to the x plus the k, where the k is whatever shifts it up or down. Remember, if a is negative, it would be flipped over the x-axis. So if I'm graphing this here, my first one is at 0, right here, 0, 5. After 1 day, there was 10. After 2 days, there was 20. After 3 days, there was 40. After 4 days, there was 80. After 5 days, there was 160. And so we get something that looks, it kind of looks like half a parabola, but we'll find out it's actually not half a parabola. We'll find that out in just a moment here. We're going to find that out right here because 2 raised to the x, well, let's start with just our basic graph here. If I plug in -2, 2 raised to the -2 is the same thing as 1 over 2 squared, which is 1/4. 2 raised to the negative 1 is 1/2. 2 raised to the 0 is just 1. 2 raised to the first is 2. 2 raised to the second is 4. If I go 3, 2 raised to the third is 8. So I'm going to get something looking kind of like this. 2 raised to 0 is 1. If it's the negative 1, when x is negative 1, we get a half. Then we get a fourth. On the other side here, we get 2, and then 4, and then 8. Just like this. So what we're going to be getting here is something that kind of looks like a plane taking off. Now a lot of people wonder, and they say, hey, when will it equal 0? This function actually never equals 0. No matter how far back I go, if it's 2 raised to the negative 10, it's going to be 1 over 2 to the 10th, which is always a fraction. It never reaches 0. We have what's called an asymptote here. It gets infinitely close, but never touches it. So there's an asymptote at y equals 0. An asymptote. It gets close to it, but never actually touches it. So we got what looks like a plane taking off. Now, if we have to graph y equals 2 raised to the x plus 4, well, we can make a chart like we sometimes do, or we can just shift everything up 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And that means the asymptote also shifts up as well. So our new asymptote here, it would be at y is equal to 4. Now, since there's no restrictions on the domain, we can plug any number in here, any negative number or any positive number into this. The domain is going to be all real numbers, or you could write it negative infinity to positive infinity. The range of our original one right here, well, we have it never quite equaled 0, but we got really, really close. So we have all numbers from 0, it goes all the way up to infinity, but never quite touched 0, so we're not going to include that. Soft brackets there. Or you can also say y is greater than 0. If we were to look at the next one right here, y equals 2 raised to the x plus 3. If we start with our original again, we're going to get here half, a fourth, 2 squared, 2 raised to the first, 2 raised to the fourth, 2 raised to the second is 4, 5, 6, 7, 8. Once again, it's going to get infinitely close to 0, but never actually touch it. And if we shifted it up 4, 1, 2, 3, 4, right there. Our asymptote will be up 4, right here. So our graph's going to be looking like this. Now, when we have the plus 3, that means we have to shift everything over to the right 3. So 1, 2, 3. I'll do this one in red. 1, 2, 3. Half over 1, 2, 3. Now these actually wouldn't cross. So we just shifted everything over 3. But once again, we can also look at this as 8 times 2x times 2 raised to the x plus 4. If I plug in 0 here, that's going to be the same as 8 times 1 plus 4, which was 12. Hey, same number right there. So this 2 raised to the x times 2 raised to the 3 plus 4. We know those are the same because just adding the exponents, those are the same. So this is really 2 raised to the x times 8 plus 4. But then by order of operations, y is equal to 8 times 2 raised to the x plus 4. So these graphs right here are going to be the same. You can graph it, look at it either way. If you prefer the shifts this way, that's fine. If you prefer just knowing what you're going to start with right there, that's fine too. So then we ask ourselves, why is this important? Why do we even care about these graphs? Well, here's why. These sorts of graphs, these exponential graphs, they model population and compound interest. So like the population of Greencastle, we can model that using these graphs. We can model compound interest as if you're saving for retirement. This right here is probably has the most application to the average student. For example, let's say you put in $500 for retirement, and that increases at 10% per year. We're going to make a graph to see how much it's worth in T years. So the principal, or the starting amount, is going to be $500. That's our starting amount right there. And every year we know it's going to be increased by 10%. So we started with, if we're the same, we'd multiply it by 1. But we're increasing it by 10%. So we're going to add on 10%. So we can rewrite this 500 times 1 plus 0.1, or 1 plus 100% plus 10% is going to be 1.1 raised to the t. And I'm going to pause here, flip over to my computer, and we'll see what that graph looks like. So graphing this on Desmos, 500 times 1.1 raised to the x. So we started with $500 way down here. In 5 years, how much is that going to be worth? Well, if I slide along my graph here until I get to 5, I can realize, hey, it's going to be about $805. Not too bad. And remember, this going to be our retirement money. So what if I left that $500 in there? Let's say I got that for graduation, and I left that in there for, how about 40 years? That $500 in 40 years turns into about $22,000. Let's say what if I left it in there for another 5 years? You get this exponential growth here. You can't really see it. get to 45 years, that $500 turned into $36,445. All from an investment you made back when you were 18. So this is why these graphs are extremely important. Now we're going to look at another application for what's called exponential decay. This is exponential growth because it's growing. Exponential decay is when the graph's going the other way. And we're going to look at that now. So if this is an exponential growth model, where it's going up like this, exponential growth, what happens when something decreases and goes down in value the opposite way? That's called an exponential decay model. And this is normally modeled in the following situations. Carbon dating, if you want to find out how old a rock is, or the half-life of radioactive elements for dating purposes. That's normally modeled by exponential decay. And decreasing car value. For example, a car on average loses 15 to 20% of its value each year. Let's say you just got a $24,000 car and it's going to decrease 17% in value every year. Your car doesn't get worth more, it gets worth less over time. So we have a starting amount of $24,000. And to find out its value after 1 year, we would multiply it by 17% and then subtract that. In other words, we multiply that by 100% and subtract 17% of its value. Then if we did that another year, we'd multiply it by the same thing. So for example, here's the value of your car. Starts off at $24,000 in year 0, right when you buy it. After the first year, we're going to multiply it by $24,000, but we're going to multiply it by 83%, 17% less. After 2 years, we'd multiply it by 24,000 times 83%. So that's what the value was last year, times another 83%. In year 3, $24,000 times 83% times 83% times 83%. So it's going to keep getting smaller and smaller. You can always tell the difference between exponential growth and exponential decay because if this number, the base, is greater than 1, it's a growth. If this number in here is less than 1, then it's exponential decay. So our model here is going to be, the starting value is $24,000 times 100% minus 17% is 83% raised to the t. So we're going to find out what, we're going to graph this and then use the graph to figure out how much is this going to be worth after 5 years, 10 years, etc. I'm going to head over to the computer now. So if we graph this, we're going to see that at time 0, it was $24,000. That's when we bought the car at time 0. And now after 1 year, close to a year, it's worth $19,920. So it's gone down by over $4,000 the first year. After 5 years, that $24,000 car is only worth $9,454. Now this is normally about the time a lot of people pay off their car. But in the meantime, they still owe quite a bit of money on it. After 10 years, your car is worth $3,724. Now you'll notice it gets really, really low, but never actually quite gets the value of 0. Now, this model isn't perfect because we actually know that a car's value, that's actually probably going to hover around, if it's worth hardly anything, it's probably still going to be worth about $400 just for scrap metal and parts. But this model here just keeps taking it out farther and farther and farther. It's getting lower and lower, get down to 1 here. There's some rounding errors in there, but it's going to get really, really low. But notice here the big drop from at time 0, where it's $24,000, to 5 years later, your car has lost $20,000. Not $20,000. $14,000 in value, $14,500. This is actually a big argument why you always get a used car, because if you can get a used car for something 5 years old for $9,454, after a few years there, 5 years, your car has only gone down to about $3,000. So you've gone from something close to $10,000 down to something close to about $4,000, $6,500, $6,500 loss compared to going down $14,000 in 5 years. So that's why these graphs are extremely important, why you should learn them, and how you should graph them. If you get some weird numbers like this, by all means, put it in Desmos, graph it, and take a look at it. Use the graph to help you figure out any information. If you just get a basic graph, though, make sure you know how to use graph the basic exponential function. Once again,